All right. Apparently people like review less, but I guess this should be quick or at least give you a good idea of what the midterm will look like. Speaking of the midterm, hey, they didn't fulfill my request. Joy. So the midterm is March 1st at the original time in that crappy room. So, yikes. So, yep.
Can you remind us what's the original time?
Sorry?
What's the original time for the midterm?
Original time was like 6 p.m. March 1st.
Okay, thank you so much.
Yeah, so the midterm will actually start at 6:30. So to give you time to because some of you might have a midterm that ends at 6, so give you half an hour to make it, go to the bathroom, do whatever. So be like 6:30 to 7:45, so that'll be fun. Sorry about the room, not my fault. I asked, they ignored me, so I guess we have to live with it. So speaking of the midterm, we'll just do a quick recap of everything we learned, do a sample midterm, and then feel better about the midterm because it probably won't be too bad. So again, 3 major concepts in this course: virtualization, concurrency, and persistence. And so far, we've only really gotten into virtualization, but we've learned a fair bit about it. And next week, we'll start virtual memory, and that will also, of course, be on the midterm, and that's generally where things start going even more downhill. But hopefully, we have enough processes typically catch people up, so hopefully we've got enough practice with that, and especially in Lab 2, you'll get lots more practice with processes, and don't try and overcomplicate Lab 2. So you don't have to create pipes or do anything like that. That's all done for you. If the test case uses pipes, it creates its own pipes. You just have to set things up nicely and kind of see the weird thing Visual Studio does. So first concept we saw, what the kernel was, and it was essentially any code that ran in kernel mode, because on our CPU there's different modes of operation that give you access to different instructions. There's user mode, which has been all your normal processes run in user mode. It's everything we know and love. And then our CPU also has a kernel mode that has special instructions that can interact directly with the hardware, do some fun memory stuff that we'll see next week, and all that sorts of fun stuff. And there was a nice interface between them. There was that system call interface that transitioned you from user mode to kernel mode. And we saw every program has to use this interface. And the nice thing about that was, well, we have this nice little tool called strace, which will tell us everything a process does. And we can go ahead, no matter what language it's written in, doesn't matter. We can see what it's actually going to do on your machine. For the midterm, we don't care about the file format of ELF and any of the details. That was just so we understood every single byte, so you don't have to worry about that. But you should know the difference between API and ABI and how we broke an ABI. And just the different kernel architectures. So a microkernel versus a monolithic kernel that just has all the responsibilities versus a microkernel that has the minimum set of responsibilities, which the minimum set of responsibilities is basic IPC, scheduling, and managing virtual memory, which again, we'll see next week. So we went through processes, Unix systems, just clone processes. Every process has a parent-child relationship. You can only create a new process with fork, and after the fork, both processes are exactly the same. The only way to tell them apart is the return value of fork. So in the child, it will be 0. In the parent, it will be greater than 0. And that will be the process ID of the child. And then at that point, you're up to the scheduler. The scheduler decides when to run either process. And in Lab 3, that will be coming much in the future, you will also be doing a little bit of scheduling. And it will be lots and lots of fun. So on top of that, creating processes, well, you have to properly manage processes, which is Lab 2. You're basically just managing a bunch of processes. So operating system has that strict parent-child relationship. You should be able to identify and prevent zombie processes and orphan processes. So your lab 2, the idea is you won't have any zombie processes because the idea of that library is it's a very good and responsible parent, so it will definitely wait on all the children processes. And for orphan processes, that's the extra like 20% of the lab where you become the awful name sub-reaper, and then you can actually adopt a bunch of different processes too. So that's like 20% of lab 2. So then we saw basic IPC, read-write system calls, just read some bytes to somewhere. File descriptors are just numbers. If it's easier to think of a file descriptor from like the last lecture, think of a file descriptor as kind of a pointer, so it points to something. So whenever you fork, you have all the same file descriptors in either process, and then after the fork, they're all independent, but they're all essentially pointing to the same things. So that's why you can actually share some. So they share the pointers are independent, but what they're pointing to is actually shared between the processes. So we saw redirecting file descriptors for communication through like opening files, so we can replace file descriptor 1 with a file, and suddenly our program just outputs to a file instead, which is kind of cool, and you can do all sorts of shell tricks with that. And then we saw in the other example where we messed with pipes to replace the file descriptors with pipes. So, and then we saw signals too, so they're like interrupts for user processes. The kernel has to handle 3 different kinds of interrupts because they'll also come from hardware. In user mode, all you deal with is signals, and they can come from hardware, but they don't have to. So we saw that you get a signal if you get, if one of your children perish, you get a signal if someone presses a keyboard, you get a signal if someone wants you to exit, and you also get a sig kill if someone really doesn't like you, and then you have no choice, your process is now done. Then we saw scheduling. Scheduling, at least the first lecture, was pretty basic. It just had some trade-offs. So we saw first come, first serve. Most basic scheduling algorithm. Think of being at a line at any store or anything like that when you go to cash out. Then we saw shortest job first, which prioritizes processes that have the shortest job first in order to minimize waiting time. So how long all the processes combined wait together. Then that was for non-preemptible processes, so we can't switch between them. And then we saw, well, what about if we can preempt processes and actually switch between them? So that was when we tweaked it, we did shortest remaining time first. So whatever process has the least amount of time left to complete, then we would go ahead and switch that in and start executing that. Again, most of these are just done after the fact because in practice, we don't know how long a process is going to live for. And it may request some resources that it needs to wait for, and it's way more complex, in real life. Then we saw round robin, which optimizes fairness and response time, but we saw there was some kind of engineering trade-offs with the quantum length, or basically the length of the time slice. So if it's short, you get better response time. Everything cycles through quicker, but you also context switch more, so that's the act of switching between processes, which is essentially just a waste of CPU time. So if that is too high of an overhead, so in other words, you're spending too much time switching between processes, then that's a bad thing. So you don't want it too small, and you don't want it too large, because if it's like infinitely large, it's essentially first come, first serve, which is bad, has all those problems, starvation being like a major one. Then we saw more complex scheduling that just added more features. So we saw there's a priority feature. We could screw ourselves over because if processes depend on each other, well, if a higher priority process depends on a lower priority process, then that's what we call priority inversion, because we should at least temporarily treat that low priority process as a high priority process because of that dependency. And that can go on forever. There's also different trade-offs depending on the processes. So if you're interacting with the processes, you want it to be interactive, be good, get a quick response out of it. While others, you might just care about throughput, like how many you can complete in a day or something like that. So you may have different goals between processes, and the operating system would know about them necessarily. Then we saw, well, that was just all the complications for having a single CPU core to schedule things, and then we introduced multiple CPU cores. So we could just do the same thing, but that's bad, or we could do a scheduler per CPU core, which is a bit better, but you might get some imbalances, and then we saw a way to deal with that by just, changing what processor or what core a process is running on, just depending on how busy things are. Then we saw the completely fair scheduler, which tries to model ideal fairness of just giving every process an equal amount of CPU time, and that's like the actual scheduler used in Linux, and most of the other systems are going to have something similar. Then we saw libraries, so that was good because Lab 2, hey, you're making a library. So we learned what a dynamic library was, how to compare them to static libraries. Static libraries are basically just a collection of code, and when you compile your program, everything gets copied into your executable, so you can't change anything from then going forward. You'd have to recompile if there was any changes, while a dynamic library will just look it up at runtime, and if you update the library and you run your program again, you use the updated library, which is both good and bad depending on who wrote the library. So we saw that if you break an ABI in your library, really bad things are going to happen, and you can't expect anything to work anymore. So if you do have a library that you depend on and they break that, you will have a very difficult time debugging. So there's like kind of an ebb and flow with what programmers prefer, if they prefer static libraries or dynamic libraries, and it seems to just cycle every few decades or something like that. So some people like static because it will work until someone, bricks it. Then they have to static just works until everything gets like super, super out of date, and then people start complaining. And then they'll switch to dynamic where they get all these updates, but then everyone starts doing that and they write really crappy code and then they break everything. So everyone is like, oh yeah, I want things to be the same again. And that cycle just kind of continues forever. All right, so let's get into the midterm and something more fun. So that's the link, that's the latest midterm I have written. So this is like the style of things I do. This was closed book, so yours is essentially open book where you get a piece of paper that you can do whatever you want. The only reason it's not open book is because I don't want you to kill like 10,000 trees. So one piece of paper is essentially open book, and actually gets you to study a bit too. So the only thing we can't answer already is the virtual memory question, which is last. So we'll skip that, and we should be able to answer it next week. All right, so here it is. So there's just starts with like a few, like 1 or 2 sentence, quick, short answers, like what's the concept of virtualization? How does it apply to operating systems? So that's just making something believe it has access to all the resources when it might not. So we don't know about virtual memory, but we don't know how it's actually implemented, but you can actually still talk about virtual memory. So with virtual memory, all the processes think they can access the entire range of memory when they actually are sharing physical memory. You could apply the same thing to a virtual CPU. A process just thinks it's the only thing running on the CPU, when realistically they're all sharing the same CPU cores. Then the next one was just kind of an easy one. So what service would you find in a monolithic kernel that's not in a microkernel? So microkernel, the basics that a microkernel has to do is scheduling, which is like switching what processes to run because it needs to maintain control and be in that more privileged mode. Then virtual memory it has to do in basic IPC. So if you take the opposite of that, well, things that would be in a monolithic kernel but not a microkernel are like file systems, device drivers, or advanced IPC. Then last one, What should you use to monitor all system calls a process makes? Hey, strace. And then next one that we saw yesterday, if you include a C struct in your library's header, why shouldn't you ever trade it or change it? And the answer to that is, well, you're essentially changing the ABI of your library because the way C lays out that structure in memory depends on the order of the fields. So if you change the order of the fields or anything about the struct, it will change how memory is laid out. And if you give that to if you put it in a header file or something like that, and someone uses that, well, they're going to compile that. Essentially, they're going to compile that version of the struct into their code. And if it doesn't match what's in your library's code, then really bad things are going to happen. So you either have to hide your struct and just give it a pointer, which, remember at the beginning, the solution to everything in computer science is just add another layer of indirection. So that's essentially making a pointer, hiding things, and adding another layer of indirection there through pointers. And then 5, what are the 2 responsibilities of init? So we kind of know this now. So its first job, we know that when you boot up your kernel, all your kernel cares about is launching a single process. And then as far as the kernel is concerned, its job is done. So it creates process ID 1, which is generally something called init. And then init has to make all the rest of the processes or, through grandchildren or something like that. So, and then its second job is it's kind of like the default orphanage or however you would want to say it, or reaper. So it has to acknowledge all of the orphan processes that that it may receive. So it just kind of it creates some processes and then infinitely calls await. And then the next one was page replacement, which we haven't got into yet. All right, so this one should be more fun. So here's some code. Can we still see that? So here's some code. Because this was closed book, I said what fork does in the problem, but I guess since here's open book and you've been doing lab 2 and a bunch of stuff, I don't have to tell you what fork does. So copy of the current running process, everything's the same. Greater than 0, process ID of the child. If it's 0, it's the child process. And then I said what wait does, but we kind of know what wait does. So we don't check, and in this I didn't check return values or do anything like that, we just kind of ignored it. So what were our questions? So our first question was, how many processes get created? So anyone want to hazard a guess how many processes actually get created here, not including the original one that starts executing? Yeah. 3. Anyone disagree with 3? Same guy. So yeah, the answer is 3. So why is it 3? So, oh, that is not for you. Okay, it closed it. No, it didn't. Okay, so why is it 3? So through the question I said, one way to argue about it to make it easier to argue about it is the first process that starts executing main is process ID 100. So we'll have process 100 here, and it starts executing main. And we don't count that towards the newly created processes. So it comes along, first thing it does is call fork, which creates a new process. So we get a new process, probably called, so in process 100, we'd create a new process called process 101, likely. And then, well, the only difference is the return value of the fork. They're copies. Doesn't matter at this point because they're both essentially there's nothing that executed, main just ran. So in process ID 100, the return value of fork would be 101 because that's the process ID of the new child. And so PID1, would be 101. And then in the child, PID1 would be 0 because that's the return value of fork. So now we would essentially have 2 processes, 100 and 101. after the first PID1 value gets set. And then at this point, you don't actually know what's going to run first, so we can just pick one at random. It doesn't matter. So let's say process ID 100 runs first. So sorry, that's 101. So if process ID 100 runs first, well, it's going to call that fork, create a new process. It's going to be process ID 102 probably, and then it would set its value of PID2 equals to 102. And in process ID 102, well, it would be a copy of 100 at the time of the fork. So it would have PID1 equal to 101 because it just copied it. It existed before. And PID2 gets set after the fork, so it is its independent value, and it's the return value of the fork, which in the child would be 0. So then at that point, PID, or process 100 and process 102 are both here. And then process ID 101 would probably execute, call fork, create a new process called 103. And the only difference, and it's a copy at the time of the fork, so PID1 equals 0. And then that's the only thing that gets copied. And then after the fork, well, we set the value of PID2. So in process ID 101, PID2 would be equal to 103. And then in process ID 103, PID2 would be equal to 0. So now, we process 100, process 101, process 102, process 103. And they are all at this point. And we've made it through all the forks, so that's all of our processes. So process ID 100 was our original, and it spawned 3 other processes, 101, 102, and 103. So any questions about that? And if we'd like draw the parent-child relationships, well, process ID 100 was the first process, and then first it created 101, which was its direct child, and then afterwards it created 102, which was its direct child. And then process ID 101 is the one that created 103. So 103 is a direct child of 101. So that's kind of what all our parent-child relationships look like. So any questions about that? Okay, then we essentially have, we have our 4 processes in total, and let's see the other questions. So here we go. So how many new processes get created? 3. Does process ID 100 or any of its children create any orphan processes? And why or why not? So the answer to this is new, because the first process creates 2 children, and then we can see that, well, process ID 100 would call wait 1 time because process ID 101 here, it would execute because we're looking at its value. Its PID 1 is 101, so it would wait once and then wait for 101 to die. And then the next thing it would do is go into here because PID2 is greater than 0, so it would wait twice. So it has 2 children, 2 waits, so that matches up. So it wouldn't create any orphans. Then process ID 102, well, here it has 1 child, so it has that 103 child. So 101 would would process ID 101 go into this if branch? So process ID 101 would not go into the if branch because PID1 equals 0, so it skips that wait, but PID 2 is 103, so it would go into that branch and call wait. So one child, one wait, all good. And that's actually all the waits we need, but we can, so it doesn't create any orphans. But then there's the last part, which says there's an issue with this program. When you run it, it seems fine, and that's because we don't check for any errors. What's the issue and how could we fix it? And you can just describe what you need to do to fix it instead of writing the code. So can anyone guess what my issue is? What error would I actually see if I like exhaustively checked all the system calls and all the errors that would happen? And I'll give you a hint, it is related to that orphan thing. So we checked these two processes. So the hint is, what would this process do that is kind of weird? Yeah. Yeah, so process ID 102, well, its value of PID 1 is 101, so it would go into this branch and call wait. And does it have any children? No, so it probably shouldn't have called wait. If you actually checked for errors, wait would have returned an error that said, hey, you don't have any children. So why the hell are you calling wait? So that's essentially our error. And to fix it, well, what we could do is just make sure we just call wait once. So the easiest fix is if we detect we are the new child process, we just reset PID 1 equal to 0 because it just means we're the child process. Or you can do any number of things just to make sure you don't call wait more times than you need to. So fairly easy fix. So any questions about that? Okay, cool. We'll look up more then. So here's some basic IPC code. So this is.
Sorry, can I ask a question?
Oh, yep.
So you say that we can, for the children, set PID 1 equal to 0, but like if we have that line of code anywhere, wouldn't like process ID 100 also run that code? Because I guess like yeah. Anyways.
So process ID 100, like if you just look at what process ID 100 does, it starts executing main, calls fork, which creates a new process. So it would get, and then fork would return the process ID of the newly created child, and we just set PID 1 equal to that. So if we just go about, so let's just assume process 101. So all it's going to do is call fork, and then fork would return 101. So we set PID 1 equals to 101, and then it would call fork again, creating another child, and then this fork returns 102. So PID 2 equals 102, and then just keeps going. Yep. Yep. Yeah. No, because if you set your variable, you're independent, right, because of the fork, so you wouldn't affect the first original process. Yeah, so anything after the fork, remember you're independent. I'm only getting the value of PID 1 because it already exists by the time I fork. For every case except the first one where PID 1 doesn't exist yet. But like we saw, any changes you make after the fork, independent in the processes. Because remember we had that example where we even printed the address of some variable. and it was the same in both of them, and we changed it in one, and it didn't change it in the other. Yep.
So what would it do that like it's waiting for a child? Would it like wait forever?
No, it just gets an error from the wait system call that says you don't have any children. So it just boots you out immediately, which if you check for errors, you might encounter that in lab 2 if you have screwed up your code. So that's why it's good to check to errors, because if you have too many wait calls, that's not good. And depending on how you do lab 2, you might actually expect to, at some point, encounter that you have no children left and there's no other way to know other than reading the error and knowing that you got the correct error. So there's there's at least 2 major ways to do lab 2. So you get to pick your poison. So that should make lab 2 more fun. All right, any other questions? Yep.
Question about the wait function. So I'm still confused about like how that piece of code allows the parent to wait for the child. Like you're just declaring like a int variable called wstatus, and you're calling wait that variable. What is the mechanism behind it that allows the parent to wait for the child?
So wait's just a system call. So the kernel will go ahead and not return that for the usual wait until a child is dead. So W status is just a way to get like all the information out of a dead process back to the parent. So in this case, it would write a value to it, but I never use it. So in lab 2, one of the things you have to do when one of the child processes dies is tell me its exit status. So you would actually need to go through and read all of that like we showed in the examples.
So if you don't care about anything that's written on the status, you can just call wait without any like input there?
Yeah, in fact, I think I could have called wait with just null. So yeah, but a good thing to know is that wait by itself will wait for any of the children to die, not a specific one. And if you want to wait for a specific child to terminate, then you use wait PID and then give it a PID argument that you want to specifically wait for. Or if you want to turn wait PID into wait, you give that PID argument as -1 and it'll wait for any child. Okay, any other questions about this? Okay, the next one. So we got more code. More code, more forking, more fun. So in this, at least reading it real quick, well, it looks like thankfully it's written in such a way that it doesn't hurt your brain through fork. So the main process would go through, essentially create a pipe, and then fork, and then the first child would go ahead, mess with some file descriptors, and then exec, so we don't have to argue about the child anymore. Then the main process would continue along, create a new process, which eventually calls exec, and if it's the parent, it just closes and then waits for 2 processes, which makes sense because our original main process creates 2 processes, it waits 2 times, and we don't care in what dies in either order. So that's assuming no functions fail. So it says we compile the program on the previous page, execute it as a new process. Again, assume that the system calls don't fail for whatever reason, and then one process becomes ls, one becomes wc, which is just like a word count program, but we don't even have to know about that. So explain how they communicate, how the 2 processes communicate together. You should explain in terms of each process and read and write system calls. So since they both operate on file descriptors. So how do these processes communicate? And what is the communication? Yep.
So they use a pipe, and it looks like the second child is
Yeah, so the way this works is, well, we create a pipe. Oh, here, I can draw a better pipe than that. Wow, look, pipe. So we create a pipe, and then we have a right end of the pipe, which would be FD1. And then anything we write to it, it pops out of FD0. So we have a pipe that's, managed by the kernel. And then we create two processes, and in the ls process, well, in ls, we make its file descriptor 1 point to FD1, and then the rest of them are all kind of default. So yeah, in the ls process, the first child, we would dupe to FD1 to file descriptor 1. So we're essentially replacing whatever was file descriptor 1 to point to the right end of our pipe. And then we close it so we don't have any extra file descriptors open, hopefully. And then we execlp it. So whenever that process tries to write to standard out, it writes to the right end of the pipe. And that will just go start filling up this pipe with a bunch of stuff. And then in the second child, well, what we do is it has 3 of the standard file descriptors, which we so far haven't touched. And then the dupe2 call would replace file descriptor 0 to essentially point to the same thing as FD0, which would be the read end of the pipe. Wow, that's a big eraser. So we set it up so that it gets the read end of the pipe before we exec, so that anytime it tries to read from standard in, it would do a read system call on that, and it would read from the read end of the pipe and get anything that the other process writes to the other end of the pipe. And then in the parent process, well, it closes both ends of the pipe because it doesn't actually need the pipe, it doesn't use it, and then it calls wait twice. So, oh, okay, so that's the first part of the question, explaining that, hey, we set up the pipe so that in both the processes, if it writes to standard out, it fills up the pipe. If the other one reads from standard in, it reads from the pipe and empties it. So any questions about the first part? So we are good with pipes. Okay. Then the worst part is when you run this program, it looks like it hangs. So I give you a hint. Oh, yep.
I had a question, but
Yep.
there were also 2 questions in the chat.
Oh, sorry. I'm bad. Will the second, oh, there's a question. Will the second if statement be executed twice? The answer to that is no. So the second if statement, or which one? This one? So this one will not be executed twice. So what's going to happen, we can give things numbers again. So process ID 100, we'll start executing our program. Normal C execution, so it gets some space. Wait, so just out of curiosity, where does it allocate space for that file, those file descriptor ints, that array? Yeah. The stack. Okay. It's everyone good with the stack when I say it like that? So they get allocated on the stack? Okay. So those get allocated on the stack. That, like them telling you in first year, doesn't matter right now, but trust me, it's going to matter because when we get into more advanced topics, that distinction will definitely matter. So these get allocated on the stack. And then our main process creates a pipe. It would fill in those values with whatever as part of the pipe system call. And then process ID 100 calls fork. So it would create process 101 probably. That is not. It would create process 101 where they were both exact copies of each other, including what all the file descriptors it had open, everything it points to. So this would have the pipe open. It would also have, the values for FD0, FD1. They're the same in both processes. And they would probably be 3 and 4. And then process ID 100. So in process 100, PID would be equal to 101. And in process ID 101, PID would be equal to 0. So only 101 would go into that if branch. And when it goes into that if branch, it's not coming out. So it goes into that if branch, messes with the file descriptor, and then calls exec_ve. So remember what exec_ve does is it transforms this process and starts executing another program. So process ID 101 would hit exec_lp, and I said assume that, nothing fails. So it would exec_lp ls, so process ID 101 would just become ls and start executing that program ls, and then it wouldn't ever return from exec_lp because it's executing something different now. It's not executing your code at all. So it would never return from exec_lp, so process ID 101 would not hit the second if branch because it doesn't exist anymore. It's executing something else. And then when ls calls exit eventually, which terminates the process, that process is done, so how could it ever get back? Then other one, say we have a parent with 2 children. If a child writes to the pipe and will the other child be able to read from it? So in this case, we set up our 2 children. So we do have 2 children. We have, process 101, which would be ls, and then process 102. Which would be WC. And we set it up in such a way that when process 101 writes to the pipe, process 102 will see whatever it writes to from the read end of the pipe. So we created 2 child processes, set them up so that they can communicate. So our communication is between our 2 child processes. And what we saw last lecture when we had a sub-process is we just communicate to our child directly. So there was parent-to-child communication, which was less steps. And in this case, we're essentially making the children communicate together. So, yeah, sorry. So hopefully that answers that. Any more questions about that? Yep, first.
So after you call exec_lp, the process will never see the rest of the program anymore?
Yeah, if exec_lp succeeds, this process starts executing a different program. Okay. And yeah, the process ID will stay the same, but that process will end whenever that ends. So it starts executing something completely different, so it never returns. Yep.
This might be tying into the second part of the question, but why aren't we closing the file descriptors when we don't use children?
Yeah, so that is the second part of the question. So yeah. So let's go to the second part of the question, which just says, when you run this process, it looks like it hangs. Why? What would you do to fix it? So we got the fix. So the fix is that, hey, I didn't properly close my file descriptors. So, yeah, so here I didn't close FD0. And in here, I didn't close FD1. But the major problem there is, well, which one of those missing calls caused my program to look like it hangs? Because one of these doesn't really matter. The other one's really important. Yeah. Yeah, so answer is this one is the important one. So the right end of the pipe is the important one because remember, if you're consuming things and you're just reading from standard in over and over again, the only way you know you're done is if you get a 0 out of that read call, which means, yeah, in the context of pipes, means that, hey, there's no one available, no one's alive to write any data to the pipe. It's not possible to get more data. So whenever you empty the pipe, nothing else is coming in. So it's closed for business. So if you don't close file descriptor FD1 in that same process, well, that's the right end of the pipe open by the same process, which is really annoying. And it's just not going to ever finish because someone has the right end of the pipe open. So that read will just sit there and wait and be like, yeah, just wait a bit. You can have more data coming in later. So I need to close file descriptor 1 in the second child in order for it to know that nothing else is possible from coming out of the right. And it'd be good practice to also close this one because I don't need it anymore. Yep.
Just to clarify, like say the second if statement, you say like close FD0, but then like you called dupe so that 0 is now like FD0, like on the right that you wrote.
Yeah.
But then after you call close, it doesn't affect that 0 at all.
No. So yeah, so the question is after I call dupe and then I close FD0, am I not affecting FD1? Or sorry, FD0? Yeah, so it makes it a bit easier to visualize it, I guess, if you kind of consider the file descriptors as pointers. So right before I do any dupe2 calls, it would probably look something like this. Where file descriptor 0 points to the original 0 whenever the process got made. I don't know what it actually refers to. 1 is original 1. 2 is original 2. 3 is the read end of pipe. And then 4 is the right end of pipe. So what dupe2 will do is essentially take this argument and make it point to the same thing as FD0. So in this case, FD0, here I'll put the numbers here. FD0 would be 3. So if you go through the value, it's like make 0 point to the same thing as 3. So I would take 0 and then I would point it to the same thing as 3. And then it would also close 0. So before it did that, so this would now be gone. There's no way to get it back. So it makes 0 point to the read end of the pipe, and also 3 is the read end of the pipe. So I have 2 file descriptors actually point to the same thing. So if I read from 3 or read from 0, I'd actually be reading from the same thing. And then the close of 3 essentially would just remove that entry. Whoops. It would just move that, sorry, it would just remove that pointer. So I still have a way to access the read end of the pipe through file descriptor 0. But now, if I try and access file descriptor 3, it's now no longer valid because it's closed and you can't, it's just gone now. And then if I remove file descriptor 4, I would just be removing that. And that was the only reference to the right end of the pipe, so now nothing references the right end of the pipe, and you can't get it back anymore. So, any more questions about that? It's probably easier to think of file descriptors as kind of pointers, and then when you fork, you have the same set of file descriptors and they all point to the same thing. But afterwards, if you do dupe twos or close or whatever, you do it on your set of file descriptors, whatever process that is. So process ID 102 here, closing its file descriptors doesn't affect the main original process. Its file descriptors would be untouched. And it's in good form that you close any other open file descriptors, so your process only has file descriptors 0, 1, or 2 open, and there's no other garbage open. And you'll see that VS Code does not follow that, because one of the things you have to do in Lab 2 is close any file descriptors that are already open. And you'll quickly discover some garbage that's open. And yeah, you can discuss it on the Discord, because spoiler alert, you'll have, I think, file descriptor 19 and 20 open, because VS Code, I don't know, it's written by Microsoft, so they're not very good at Linux. All right, I guess that's it. We're at our time. So just remember, pulling for you. We're all in this together.